This is Jose Garcia with Lecture 21, MET 334 Advanced Fluid Power, and we're going to start an introduction to pneumatic systems today. So, some things to consider, general things about pneumatic systems is that, of course, the fluid is highly compressible. It has low viscosity and low density. And so, in the next few slides, I will tell you what that means in terms of putting together a system. So, if you recall from lecture 2, compressibility is the inverse of the bulk modulus of a fluid. And the bulk modulus is a fluid characteristic that tells you how stiff a fluid is, how difficult it is to compress that fluid or expand it too if you're trying to create a vacuum to pull it out. And so if you remember from lecture 2, we defined the bulk modulus as the change in pressure, the change in volume with respect to the change in pressure, which is compressibility. And then that's 1 over the volume, which means per amount of fluid, per volume. And so I'm sorry I used a different notation than the one used in the book. In the book, they use beta, the Greek letter beta for compressibility, which I have as C in this slide, and capital letter B for the bulk modulus, which I use for beta. I think this is a better notation, and I'm going to stick to it. And the negative sign, of course, means that when you're compressing the fluid, the volume is changing, it's contracting, and therefore you have a negative sign in there. All right, so this is just a review from lecture 2. Anyway, so now how is this important for compressible gas or air? For air and in general in gases, we use the ideal gas law for polytropic processes. Polytropic means any kind of process that goes from one state to another state, different temperature, temperature 1, temperature 2, volume 1, volume 2, and so forth. So those are the polytropic processes. And so if you want to characterize the process itself, then you follow a curve that looks like this. P, the pressure, times the volume to the nth exponent must be equal to a constant value. Okay, and that's the ideal gas law. Now, the type of process, it's signified by the n exponent. So when you use an adiabatic process, then n is equal to 1.4, which is typically used for nitrogen or for compressed air systems. Okay, now if we take this equation, the PV to the n exponent equal to a constant, and we derivate that, we use the derivative to see the change in pressure and the change in volume, then we find the definition of the bulk modulus, which is V equals dP dV. And so more interestingly, we can see that that bulk modulus is no other thing than the n exponent times the pressure with a negative sign. And so it's very easy to find that bulk modulus by just knowing the exponent value, 1.4, times whatever pressure that the system is at. It could be somewhere between 0 and 150, which is typical for compressed air systems, so that you know what the compressibility of the air at that point is. Okay. And then here's something more interesting even. You can store energy in air, and that's because the high compressibility of the fluid, in this case gas or air, then you can somehow store some of that energy. Imagine a spring or a foam, right? With a foam or a spring, if you remove any kind of force, it will recover its shape. However, when you do a liquid, the liquid will tend to occupy the space, the chamber that it's storing it. But if you apply a load to it, it will it will not deform. It will continue to be the same shape that it is. It's not compressible. But if you have air in a vessel and you put a piston to it, it will compress and it will minimize that volume until it can compress no longer. Uh, but as soon as you remove the force of that piston, it will recover its original shape and it will tend to occupy the maximum volume available. And so by virtue of that compressibility, then you can say that you can store energy in the form of potential energy. And so we have here an equation that tells us what the energy of the compressed air is. And it's just the integral of the pressure in the fluid times the change in volume from the initial volume to the final volume. Okay, and that's it. That's the energy. And so if you were to replace that using the ideal gas law, then you can find that the energy stored in air, it's the initial pressure to 1 over the exponent n times the initial volume divided by the exponent minus 1 multiplied by the initial pressure with all those exponents minus the final pressure. So you can chuck in that equation, and like I said, because air is far more compressible than oil or any other liquid, more energy can be saved in air than it could be in a liquid like oil. And there is an example, really very good example, on page 369 of your textbook, where he goes and looks into considering the bulk modulus of the gas or air in this case versus the bulk modulus of oil, how much energy can you store due to compressibility, and the difference is 1 to 3%. So basically, of 100% of energy you can store with compressed air, only 3% can be stored with that oil due to compressibility. So gas is very good, air is very good at storing energy. You can use it to save some energy. All right, some important implications of using air. Well, here's what you have to take into account when you are using a pneumatic system. The response time. Because the air is compressible and it's taking energy from the system, the response time of the pneumatic system will have a delay. And so only until you reach out a certain critical pressure to break things from moving, only then the piston will start moving. So it will have a delay that you will not see so much on a liquid a liquid system. There is also an issue with non-uniform motion for the same reason, and because there is there is that compressibility, the air will compress until it can break the friction of the system, and then it will start moving. So till then, you're just compressing the air, not moving anything. So those are potential disadvantages of compressed air systems. Now, on the bright side, compressed air systems, or pneumatic systems, they don't see water hammer. Water hammer is the chock, the audible noise that liquid systems produce when a valve is suddenly closed, and you hear that knocking on the tubes. You don't see that in pneumatic systems because of compressibility. There is that give, and then all that energy is absorbed by the compressed air. Pneumatic systems, compressed air systems, can be used as power backup because you can store that energy in a vessel, in a reservoir. You can, if you lose power, say you lose gas power or electric power, and you have some energy stored in the form of pressure in a vessel, then you can use that energy to unlock a system. And so as a backup, it can be used. Another disadvantage of compressed air is you need to use mechanical locks if you want to keep the position of the piston or the rotary actuator locked. you need to lock it with mechanical systems. You cannot use, like in hydraulics, you cannot just simply um, close the valve and then assume that the cylinder is going to stay in position. That only happens in hydraulics. You cannot do that with pneumatics because pneumatics are compressible. Um, Here's an advantage. Thermal expansion does not affect pneumatic systems as it does liquid systems, because the thermal expansion coefficient of air is relatively low compared to liquid systems. Then changes in temperature will not significantly increase the pressure of the system, therefore no significant change. Whereas in a liquid system, if you change the temperature, say by up to 50 degrees Celsius, you will see an increase up to 400 bar in a system. So that's very significant. Lower density, of course, the density of air is far less than that of a liquid, and that means less weight in your system, so that's an advantage. Viscosity of air compared to viscosity of liquid, so the viscosity of air is really very low, and therefore there is less viscous friction uh, to be broken when you want to move um, an air system. And then some other important implication: because air is clean, you can dump it back into the atmosphere without needing to have a reservoir. You can just do that and no problem, no filtration needed. Um, Compressed air reservoirs or air tanks or receivers are typically large in volume. They need to occupy a large space if you want to store some energy. It's just the nature of things, you know, because air is very compressible. You need a lot of volume to store some energy. Another thing is that air is uh, it's a poor lubricant, and that's because of the same. It's compressible. So when you have situations where you have two moving parts and air between those two moving parts, the compressibility of air will not suffice to separate those moving parts, metal to metal contact, and it will just be um, metal to metal contact without any air in between to impede that contact. Um, Air carries moisture in the form of vapor, and that moisture can find its way into metal parts and rust them. It can the moisture um, it can become liquid, right? The vapor can become a liquid, and it can get deposited in certain places. And so, yeah, that's not a good thing for any metal part in the pneumatic system. Um, Air is non-flammable, so this is an advantage, no question. However, when you have a pressurized vessel, you have to be extremely careful that if there is a puncture or if there is any foreign object that can puncture the vessel, be super careful, because this can create an explosion of the vessel. This is a compressed fluid after all, and so special care needs to be placed for these compressed air vessels. All right, and so the main components of a pneumatic system, as you can see here, well, of course, we have the, whoops, we have the compressor, which typically is powered by either an electric motor or a compressed air engine. We typically need some cooling, because when you're compressing the air, this air will get really hot. There is filtration taking place also, and a drying stage that requires to remove all that moisture from the system. And then after all of this cooling, filtering, and drying takes place, then you can regulate the pressure of the system using a regulator and proceed to store. And then every component, you know, from the storage or receiver, it's distributed to the different functions. Every function itself will have its own filter, cooling, drying application. So this symbol that you see here, it's everything in here. It's got the filter, the regulation for the pressure, and the lubrication for this system. So, and then we have here a DCV that controls the piston itself. And then just to finalize here, we have the different types of compressors. We have displacement and dynamic. The displacement ones, just like pumps, they rely on separation or isolation of the pressure chambers. And so we have reciprocating and rotary. And then the dynamic ones are the ones that do not separate the inlet from the outlet. And so we have two types, radial and axial. And so as a general rule, you can remember that the displacement ones are low flow and high pressure. You can see the compression ratio is far greater than that for dynamic ones. And they also work at lower speeds than the dynamics. The dynamics, on the other hand, they are really good at sending large amounts of fluid or flow, but they compress the air less than the reciprocating ones, and they turn really, really fast. This is just a table that it's in your book, into page 374, and table that separates the different types of compressor. That's all I have for you today. I hope you enjoyed this, making it short and simple. And so I'll post a few more lectures. We're nearing the end of the lecture topics, and I will also look into your finalizing your project for the class. What I'm thinking, in case you're curious, I don't want you to expand on your project too much, except I want you to fix some of the some of the things or the feedback that I'm going to give you very soon, and maybe create a very simple simulation of the system working, and that will be the end of it. All right, with that being said, then I will post this video. Talk to you soon.